por ejemplo, esto de la comunicación. Lo que
pues muy buenas tardes, bienvenidos todos ustedes a este magnífico recinto, el Palacio de Minería, que es la parte inicial de la historia de la enseñanza de la ingeniería en nuestro país. Estoy muy complacido por quienes nos acompañan el día de hoy en esta conferencia magna. Está el maestro Alejandro Vázquez con nosotros, es secretario de la especialidad de Ingeniería Civil, representando a su presidente, el doctor Nahum García, a quien mandamos un cordial saludo y esperamos un pronto restablecimiento. Nos acompaña también el ingeniero Oscar Valle Molina, quien es presidente del programa multidisciplinario en transporte, infraestructura y ciudades. Muchas gracias, Oscar, por estar aquí. Y pues está también nuestro invitado especial del día de hoy, el profesor David Young. Antes de introducirlo, déjeme dar una breve explicación del por qué lo tenemos hoy aquí. Yo quiero agradecer al profesor Young. Thank you, Professor Young, for accepting the invitation to take a part in a research project of my university. Lo invitamos gracias a una recomendación del profesor Dan Frangopol, quien es académico correspondiente de nuestra academia, y me recomendó que lo incorporase a este proyecto de investigación, y como parte de las actividades lo invitamos a que viniera a visitar a México y que impartiera una conferencia con los alumnos. Desafortunadamente nuestra universidad está en paro y no es posible tener acceso al campus y contacto directo presencial con estudiantes. Entonces le planteamos al presidente de la academia, el doctor Alberto Lepe, a quien agradezco me haya hecho la invitación para venir a coordinar esta conferencia el día de hoy en su nombre, y él fue quien nos recomendó que hubiese una conferencia aquí en la sede de la Academia de Ingeniería. Entonces, doble agradecimiento al profesor Young por aceptar los cambios de última hora. Entonces, a nombre de la Academia de Ingeniería y en particular del maestro Alberto Lepe, quiero darles la más cordial bienvenida a quienes están aquí presencialmente y a quienes se han conectado a través de Zoom y de las otras plataformas a distancia. En particular, en la plataforma de Zoom van a estar habilitadas las funciones de subtítulos y de transcripción para que quien lo juzgue necesario pues las habilite y que pueda contar con el servicio de traducción por este medio. Una disculpa por no tener traducción simultánea, pero bueno, pues dada la premura del evento. Sin embargo, yo también me ofrezco a que en la parte de preguntas y respuestas poder ayudar en la traducción, tanto de las preguntas que se hagan en español para pasárselas a inglés al profesor Young, como las respuestas que él nos dé en inglés para el público que quiera escuchar en español. Entonces, bienvenidos los que están a distancia. En particular, nos complace mucho contar con el grupo de la ESIA, la Escuela Superior de Ingeniería y Arquitectura del Politécnico, de donde hay algunos profesores y alumnos de la Escuela de Graduados, en particular del área de estructuras, que están conectados y que nos hacen favor de seguir la conferencia. En general,
la doctora Sandra Llegues.
La doctora Sandra Llegues, quien es la coordinadora de la CEPI, del posgrado. Sí, muchas gracias por su colaboración. Entonces, pues sean todos bienvenidos. I want to thank you, Professor Young, and double reason. First, welcome to Mexico, and accepting the invitation to come over. And the second one, for your availability to take the modification in the program. That I think is going to be for the good of the Academy. En la siguiente parte del programa le voy a pedir al maestro Alejandro Vázquez nos dé la semblanza del profesor David Young.
Me voy a permitir leer una breve semblanza del doctor David Young. El doctor David Young es profesor asistente en el Departamento de Ingeniería Civil y Ambiental de la Universidad Estatal de Portland, en Oregon, Estados Unidos. Antes de unirse a la universidad en 2020, fue investigador asociado postdoctoral en la Universidad de Lehigh, en Pensilvania, bajo supervisión del profesor Dan Frangopol, miembro de la Academia Nacional de Ingeniería de los Estados Unidos y miembro correspondiente de nuestra Academia de Ingeniería. La investigación del Dr. Young se enfoca en la administración avanzada y efectiva de estructuras y de sistemas de infraestructura civil, con un énfasis particular en atender los impactos de eventos catastróficos y/o cambio climático. Su trabajo se dirige específicamente al riesgo del desempeño de infraestructura de transporte con componentes críticos interdependientes. Otros intereses de investigación abarcan confiabilidad estructural, administración de infraestructura de transporte informada en riesgo y la toma secuencial de decisiones para sistemas de infraestructura bajo incertidumbre. Es autor de 34 artículos de journal, 6 capítulos de libro arbitrados y más de 15 contribuciones a varias memorias de diferentes congresos. Con un índice H de 24 bajo el Google Scholar 2025, fue nombrado como uno de los más impactantes científicos emergentes de 2023 por Elsevier. Recibió el premio Moissaif de 2022 por la Sociedad Americana de Ingenieros Civiles y el premio al Joven Académico 2024 por la Asociación Internacional para el Mantenimiento y la Seguridad de Puentes. Welcome, Dr. Young, and please be in your house.
Thank you for the introduction. Thank you very much. Should we get started?
Go ahead.
Yep.
Thank you.
Thank you. Thank you very much for having me. My name is David Young. So today we're going to just talk a little bit about my research. And again, thank you very much for the hospitality, for having me here. Oh, I guess we have another mic here.
Also, there's the control. Yeah, you can change your presentation.
Okay. Thank you very much. So, should I get started?
Yeah.
All right. So again, thank you very much. I arrived yesterday, and thank you for the hospitality from the Academy, from Professor De Leon. It's an amazing city, and I'm constantly amazed, impressed by the history, by the vibrancy of the city. So I'm looking forward to have more kind of interesting discussion after my presentation. Thank you very much. So today, I'm going to talk a little bit about my research, focusing on the performance risk assessment for the infrastructure system under 2 conditions. One is the so-called catastrophic events. I will kind of conceptually define what is a catastrophic event later on, but also under climate impact. So again, my name is David Yang. I'm an assistant professor from Portland State University. So a little bit. I think this one is.
Maybe it is.
Oh, here we go.
Okay. Esto.
All right. So I'm sure that's the introduction that happened just now, but just a little bit of brief introduction about my background. So I was born and raised in China, and I did my undergraduate in the city called Hangzhou. So that's in Zhejiang province. I went to Zhejiang University. So that's where, if you know what Alibaba is, that's where that city was. And then after that, I moved to Hong Kong. So my supervisor was Professor J.G. Tang. So he's now the president of the Hong Kong Polytechnic University, and he's also a member of the Chinese Academy of Sciences. And then I moved to Pennsylvania. So during my PhD, I have 2 advisors. One is Professor Tang. The other one is Professor Dan Frankopol from Lehigh University, who is also a member here at the Academy. So thank you for that connection, I guess. And then since 2020, I moved to Portland State University to start my research and teaching career as an assistant professor. So a little bit about my university. So Portland State University is located in the city of Portland in Oregon. So it's founded in 1946, so it's a relatively young university. So it's founded in response to the returning veterans from World War II. So it has an enrollment about 20,000 students, including both graduate students and undergraduate students. And we have a reasonable amount of research expenditure every year. So we are the only urban research institute that has been designated by the state. This is mainly thanks to our location. As you can see in this picture, that is, the campus is actually embedded in the downtown of the city of Portland. So there is no clear boundary where is the city, where is the university. So in this sense, we have good communication with the city, with the communities living in the city that will facilitate our research. So this is a slide just showing our department with my colleagues. This is a relatively small to mid-sized department. So we have all the traditional civil and environmental engineering disciplines, from structural all the way to environmental engineering and water resources. So the picture here are just some of my colleagues. Those are not all my colleagues, but mainly for research faculty as well as teaching faculty. So despite being a relatively small department, we do have quite a few achievements that I'm very proud of. So for example, my colleague here at the top left corner, Dr. Diane Mogg, she just received the Prestige NSF Career Award, which is quite kind of acknowledgement to her work in geotechnical engineering. So at the bottom left corner, we also have Dr. James Pankow, who is the member of the National Academy of Engineering. So in terms of some statistics, our department has on average an annual research expenditure about 2.8 million. And we're home to the largest earthquake shake table in the Pacific Northwest. So for those of you who are not very familiar with terminology or geography in the US, that's mainly Washington State, Oregon State, and part of Idaho as well, sometimes also including Alaska. So we're also home to two of the most widely used simulation models for water quality. So every summer we will have a lot of folks coming from all over the country to have training camps to go over those software. And we're home to the world's highest barometer. So that's the device that you can see, the first thing you can see entering into our engineering building. And we have, as I mentioned, Dr. James Pankow, who has been doing amazing research in environmental chemistry and water resources related research, who is the member of National Academy of Engineering. So for the research areas, so we do have the traditional civil and structural engineering research areas listed here. But one thing I do want to highlight is the engineering and preservation of existing structures, which is a new focus area that we started in 2024. So this is an area that we started with my colleague, Dr. Thomas Schumacher, to fill in the gap of traditional civil engineering curriculum that is focusing primarily on the design of new structures. So we want to have some training for the future engineers to know how to handle existing structures, specifically not only the old infrastructure, but also a lot of the historic structures, where that preservation stands for. So my colleague Thomas Schumacher just got back from a trip to Egypt, so he did the non-destructive testing for the pyramid, and interestingly found I've never known tunnel inside the pyramid thanks to their research. So that's something that we've been doing. So with that, I would like to go actually into my own research, but before that, I have to acknowledge, and I really like to acknowledge my students and sponsors. Without them, there won't be the presentation today, there won't be my my work. So huge thanks to the hard work by my PhD students, Antina and Amir, who have been working really hard to push forward our research agenda. Also, my master students, Puyan, Maud, and Ayush, they all contributed to my research agenda. And lastly, the presentation here that I am about to start are mainly sponsored by the following agencies that include the National Science Foundation of the US, the Federal Highway Administration, the University Transportation Center, the Oregon Department of Environmental Quality, as well as the SCE. A standard disclaimer there that anything that I'm saying today are opinions of my own, doesn't represent the opinions and views of those sponsoring agencies. I also like to say, despite those opinions can be true and reasonable, still they are just our own opinions. So with that, so for today's research, I'd like to focus on this so-called performance risk of transportation structures. So here we define risk in a very traditional way, that is simply the combination of the failure probability of a transportation structure or a civil infrastructure and the consequence of that adverse event. So the consequences can be measured in different performance measures. For performance-based risk assessment, we are looking at mainly the functionalities of the transportation assets or other infrastructure systems. So what you'll see here on the left are the river crossing bridges in the city of Portland, and then on the right, you see the kind of typical Monday rush hour traffic. So as you can imagine that when earthquake happens or any type of disaster happens, the performance of the entire transportation network in terms of its travel time will significantly increase. So for risk assessment, what we are trying to do is to quantify that societal impact from the damage and failure of structures. So that can be quantified by a wide array of performance indicators, coming from the simple connectivity analysis to more involved transportation analysis that demanding traffic assignment. So all those have been used by my research, and they have their own use. So I'm happy to talk a little bit more about what indicator is the best for different use cases. But no matter what performance measure you use, you will face some real challenges when you are trying to do performance risk assessment. So that brings us to the first topic, that is, what are the performance risks for infrastructure system under the so-called catastrophic events? So the events that is relevant to us in Oregon, in Pacific Northwest, is the so-called Cascadia subduction zone earthquake. So those are earthquakes caused by the subduction between the two plates, that is ranging all the way from the British Columbia, the Vancouver Island, all the way down to Northern California. So this Cascadia subduction zone have shown to be really catastrophic in the sense that it can create earthquake up to the magnitude of 9. So the last time this happened was about 320 years ago, and there is a very high likelihood that this catastrophic event may happen again in the near future in our region. So our work is trying to figure out what will be the risk and what will be the things we can do to prepare for such catastrophic events. So just a toy problem here to illustrate what are the challenges that you may face when you do performance risk assessment. The main challenge are first methodological. So for performance risk, what we call those are risks that are not additive, meaning that you cannot do a risk assessment for one structure at a time and then add them together to form your system level performance risk. So the toy problem here on the right shows that if you have this simple transportation network, if two bridges fails, by inspection, you know the traffic flow capacity will drop to 0. So the traffic flow capacity will drop from 5 to 0. So the risk is, the consequence here in this case is 5. However, you cannot recover this number 5, by doing one structure at a time analysis, no matter what performance indicator you use for that specific structure. So basically, this means that for performance risk, we really need to know the states of all the structures in my network in order to quantify the consequence. So that brings in the challenge, computational challenge. And the second challenge is, when we are talking about risk assessment, there may be cases when you have a very low probability event, but very high consequences. We call those gray swan events. So that will make traditional sampling approach, typically Monte Carlo-based approach, impractical. So again, looking at this toy problem on the right, you see that if I put a failure probability for all these 3 bridges and then do a Monte Carlo simulation with 100 samples and evaluate the system risk, there will be a high chance that you don't have any failure probabilities for bridge samples with failure of bridge 3, which will cause the underestimation of your performance risk. So that's another challenge of performance risk assessment for infrastructure system. So the other question we are trying to investigate is, so for risk assessment, we need to know the fragility models. Traditionally, the fragility model tells you, given a so-called x-axis, which here is the intensity measure of a hazard, earthquake specifically, what is the probability of a structural failure or structural damage state? So previously, for regional risk assessment, this is usually done by averaging out a group of structures and use that typical fragility curve here shown in blue to represent the likelihood of structural failure. This is okay if you are looking at economic risk, where you can add the probabilities of failures of different structures together to form your system risk, because the overestimated failure probability and the underestimated failure probability can just cancel out when you add them together. But as I mentioned before, for performance-based risk assessment, it's a nonlinear function between the risk and the failure probabilities and the consequences. So that's why we want to know what is the implications of using this type of simplified fragility curves when we are doing a performance risk assessment in terms of both the estimated risk as well as what will be the impact on the ranking of importance of different structures. So that's another question we're trying to answer here under catastrophic events. And the approach we took here is the so-called transitional Markov chain Monte Carlo, or TMCMC. So this is not an approach invented by us. So credit goes to Chin and Chen in 2007 and Betts in 2016, who first created or invented and then further refined this approach. It was traditionally used for, as you can guess, Bayesian updating, where you want to get the updated model parameters given some system output. So here we chose this algorithm for performance-based assessment is mainly its great capacity to estimate the denominator in your Bayesian theorem, which we call evidence. So later on I will show. So our contribution is to build the connection between this evidence term in Bayesian theorem and the network risk assessment that we are interested in. So the modifications that we implemented here is to adapt this TMCMC algorithm traditionally used for Bayesian updating to system risk assessment through the following 3 major steps. So first, we created a transformation function to convert the discrete failure or damage state of a structure to a continuous state using a hidden variable. So that allows us to go to the second point where the system risk can be formulated as a high-dimensional integral. And that integral, if you take a look at the second line of the second bullet point, you can see that it looks very, very similar to the evidence term that I presented previously in the previous slide. So that allows us to use TMSMC to do the high-dimensional integral to solve the risk assessment problem that will allow us to address challenges of curse of dimensionality as well as the existence of race 1. And lastly, not only am I able to know the system performance risk, I'm also able to use this approach to know which asset or which bridge is more important in terms of carrying the system performance of the infrastructure system. So if you're interested in details, I listed the paper that we just published with my students. So over there you can see a little bit more details about this approach. So we use this approach for accessibility risk assessment in our region. So accessibility risk here is mainly to evaluate the accessibility of communities to hospitals right after the what we call CSC event. So we take a very simplified approach, a modified Hansen integral index, which is essentially the inverse of closest distance from a community to a hospital to measure the accessibility. And we use the change of accessibility to show what is the risk to our communities from the earthquake. So the last question we want to answer through this case study is to see what is the impact of fragility simplification, as I mentioned before. So here we're going to compare the fragility curves from HATUS with what we call the homogenized fragility curve, which we just use one single fragility curve to represent the failure probabilities of all the bridges in the network. We want to see what is the downstream impact of that simplification. So we use this approach, the TMCMC and the two sets of fragility models for a case study in Portland metro area. So that's the boundary of our study area that includes the city of Portland, the neighboring counties, as well as the city of Vancouver in Washington, just across the Willamette River. So what you see here are the arteries and the emergency response routes within this metro area, as well as the 18 hospitals that are located in our region. So this network includes about 1,700 nodes and 2,600 links, with 664 bridges located on 461 links. So it's a relatively realistic scale. It's more realistic than a lot of the academic examples that we have been using. So for the hazard on the left here, what you see is the map of spectral acceleration extracted from the M9 project. So M9 project is an NSF-funded project that happened at University of Washington that wrapped up a few years ago. So they generated a synthetic ground motion record for the Pacific Northwest region under the CSC event. So they considered a lot of the geology factors as well as the mechanisms of earthquakes to arrive around 30 scenarios of what will happen under the CSC event. So we use this as input and consider the two sets of fragility curve. One is the HATUS fragility curve that are relatively okay in differentiating the different structural failure probabilities, and the homogenized, this blue curve here simply derived from averaging all the fragility curves for the structures in the region. So here are some results. So we can see that use the TMSMC, we can analyze the accessibility risk of our region. So if we use the hazardous fragility curve, so the accessibility will decrease by 11.6%. And the heat map here also shows the importance of different links in the transportation network so that we know, or the decision maker will know which link they need to put more resources for seismic retrofitting. For the figure on the right, what you see here are the same results using the homogenized fragility curve, where you only have that one averaged fragility curve for all the links, and you can similarly get the accessibility risk. In this case, this risk will be underestimated. Also, you will get the map of link importance. So visually, you can see that using a homogenized or simplified fragility curve, the importance links are more concentrated in the downtown core. But when you are using hazardous curve, where each bridge gives you a different failure probability, the important bridges are more spread out. So that's one of the implications of using a simplified fragility curve. And we quantified this by comparing the rankings of different bridges, by comparing the importance factors of different bridges using the Spearman correlation coefficient. So for decision making, what is really important is the top rank bridges, meaning the most detrimental, the most critical bridges in that network. So as you can see that as I put my scope of focus more and more into the upper tail of the important bridges, the correlation starts to decrease, which means that using a simplified fragility curve will not give you a good ranking of your bridges in terms of importance. So it will kind of distort how you rank the importance of bridges, will have downstream practical implications, meaning that some of the important bridges will not receive resource for retrofitting. So here give you a more specific view. So this is the top 10 bridges. So you have I don't know if you are able to see my mouse, but Portland is located in this confluence between two rivers. One is Columbia River, which is the boundary between Oregon. So the one on top in the north, that's the boundary between Oregon and Washington State. And then its tributary is the Willamette River, which separates the city of Portland to its west part and the east part. So our university is located on the west side of the river, but a lot of the residential area is located on the east side of the Willamette River. So this figure just shows you that using different fragility models, even though you have 7 out of 10 of the bridges that are similar or the same, the ranking are very different. And there are also 30 bridges that will be totally ignored if I use a really simplified fragility model. So again, the implication is that 3 bridges will not receive necessary resource for maintaining the accessibility from community to hospitals after the earthquake. So that's why it's important to have detailed fragility models. I'm not suggesting the hazardous curve is the most detailed fragility curve you can have, but it does show that when you do performance risk assessment, it's necessary to have really detailed fragility models that can differentiate different bridges within the area of interest. Otherwise, you will have distorted answers. So this is a part of this part of the work has just been presented in ICOSA 2025 in Los Angeles. So kudos to my student who did a great presentation there. Again, you can find the conference paper there at the bottom of the page. So using the same approach, what we are doing right now is to do the risk assessment for what we call the Critical Energy Infrastructure Hub in Portland, or CEI Hub in Portland. So this is referring to a stretch of 6 miles area that is industrial with all the fuel storage tanks, so those are fuel terminals. So Oregon is unique in its status for its fuel infrastructure in the sense that in the state we don't really have refineries. So here this critical energy infrastructure hub, this fuel terminal stored all the fuel need for the city and over 90% of the fuel supply for the entire state. So as you can imagine, this is a huge concern for the state of Oregon, especially considering a lot of those tanks are built before the introduction of seismic code. And to make things even worse, those are located in liquefiable soils as well. But what we are trying to do here is to consider the interdependency between the energy infrastructure, including fuel storage tanks, as well as the pipelines that's here in the figure shown in the gray curves, as well as the land transportation network that transport petroleum products or fuel to the gas stations. We want to see what is the risk in terms of fuel supply to our region when the earthquake happens. So this part of work, we are working currently with the State of Oregon, Department of Environmental Quality, or DEQ. You may ask why DEQ? This is because they are in charge of the control and mitigation of the spilling of the fuel products. So that's why it's an environmental concern as well, and then they want to make sure the tanks are seismically protected. We have also conversation with the Oregon Department of Energy to see how this type of work can be expanded to the other fuel terminals within the state. So the second part of my presentation is on the climate change impact. So the first part is catastrophic events, in the sense that you may have a lot of simultaneous failures of structures under that event. The second part is mainly focused on the challenge brought by the climate change. So specifically, although climate change, we have consensus on its global impact, but as civil engineers, it's really, really hard to know what will be the regional impact under climate change, or to make things even worse, what is the structural specific impact due to climate change, and quantify it. So that's the challenge we're trying to provide some answers. I wouldn't say I have all the answers, but it's something that we have been working on in order to see how to handle that uncertainty when we do regional or structural level analysis under climate change. So to talk a little bit about motivation here, I do want to give credits to Professor Akiyama from Waseda University, Japan, who prepared this nice slides. So he's kind enough to let me reuse this slide. So for infrastructure, so climate change can have a number of impacts conceptually. The first one is with the rising temperature as well as the humidity. So the corrosion of the rebars and a lot of steel parts in the civil infrastructure may corrode faster. So that will increase the life cycle risk under the climate change impact. And secondly, so the climate change can also change the frequency and intensity of extreme events. In this case, you have potentially more frequent or more severe wind events that may, in the worst case, collapse your bridge. But in this presentation, I'm going to focus on the other aspect of climate change that may also have rising frequency and intensity. So that is due to storm and storm surge. So storm may compromise your substructure in the form of scour. So that will create a compromised foundation that will reduce the load carrying capacity of your bridge. And also for your superstructure, the wave may also push the deck up, so that may causing what we call deck unseating, so that will also decommission your structure, causing failure and consequences. The objectives here is to be able to know what is the uncertainty brought into the picture due to different emission scenarios, what we call here climate futures, as well as global climate models. And then we want to know how to input those climate information into structural relevant information so that I know what will be the increased failure probability of different structures under climate change. And then we want to know how to capture the trend from a very wide noise due to the uncertainties brought into the analysis by climate futures and global climate models. And then lastly, we want to know how to do decision making, even though we have those deep uncertainties. So that's kind of the through line of what we are trying to answer. So again, these are the approach we're using for this two failure mode. So for the deck unseating or deck dislodging, what we are using is the actual design specifications. So this is developed right after Katrina to better analyze bridge deck failure under the storm surge from hurricanes. And for the scour failure, we were using the scour depth estimation from the Hydraulic Engineering Center model, or HEC model, to know what is the size of your scour damage under different flow discharge. So with those, we also want to tie the failure of those failure mode, from those failure mode to the climate information. To do that, what we're utilizing is the four potential, what we call climate futures that are quantified or defined by the IPCC. In their terminology, is called representative concentration pathways, or RCPs. So you can imagine those are emission scenarios if the international community choose to have certain emission policies or we are going to proceed business as usual. And on top of that, in order to know what is the impact in terms of precipitation and temperature, so there are also a global climate model, also called general circulation model, GCM. So those are used to give projected precipitation and temperature data at a global level in a grade format. So the other technique we need to use then is the statistical downscaling, because each grade in those GCM models may be larger than the state of Oregon. So how do we use those global level models for the analysis? That's the downscaling that people have been doing. So we utilized the work from other statistical downscaled data. So once we have the temperature and the precipitation data, we can then put it into the hydrologic analysis that consider the water balance and water cycle. So those are used to predict under different climate futures what will be the flow discharge that will be under the impact of climate change. So for that, we use this SWOT model that consider different aspects of the water cycle process. The result, if I can, okay. So this is the bigger picture of what we're trying to do for that part of the study. So on the right, you see is the case study region. So that's a region that when I was still working at Lehigh, called Lehigh River Watershed. So this is a region specifically vulnerable for flooding failure. So what we're trying to do here is, based on the projected climate input, as well as the land use, soil condition, and as well as the slope condition from USGS, we want to know what will be the flow discharge change at different tributaries of the Lehigh River watershed, and then put that into the engineering model for scour prediction. So that's the kind of the general steps that we're trying to take. And the bottom left figure shows you mainly the wide range of changes from model predictions from either different global climate models or different emission scenarios. And a lot of those things we do not know for sure. So a lot of things are social economical or political, so we don't really know how to predict those things. So this is part of so the study here is to show that we do face what we call deep uncertainty challenges when we are trying to do regional level analysis. This is if we then put those discharge into the scholar risk analysis, you see that you have a wide range of possible scenarios under the climate change impact. Some of them may severely increase the scholar risk, but some of them may even decrease the scholar risk. So that's the motivation for us for the last part of our study is we don't want to use those deep uncertainties as excuses of inaction. So we want to know that despite those uncertainty, what we can still do. So that's a technique that we introduced here in adaptation planning that is called robust decision making under deep uncertainty. Again, this is not a concept that we developed. This has been has rooted in military operation for a very long time. So here, rather than answer what will happen and then try to refine your prediction, so what we are trying to do here is to know what will cause unacceptable risk or undesirable consequences. So shifting the effort from improving the prediction to the decision-making process of what we need to do, despite the uncertainty. So for civil engineering, so what we did here is to use this concept to categorize the life cycle risk of structures under the wide uncertainties that we may have, and then see when and what condition the risk is likely to become unacceptable. So you may ask then, what will be that unacceptable risk? So that's where that red part kicks in, because this is putting back on my structural reliability research hat. So in reliability analysis, we have this so-called target reliability index. So what we were able to do is to recalculate or calibrate this tolerable or acceptable risk based on the target reliability index. Then I know that under different uncertainties, when I will have unacceptable risk. The underlying assumption is if the society must have tolerated some type of risk, and we want to use that implied tolerance to decide when we need to do climate adaptation actions. So we use this concept in an example. So this is that deck and sitting example that I introduced before. So on the one hand side, you may have factors that have really, really high uncertainties, such as the hazard rate, the storm surge height, the sea level rise, the precipitation change, or God forbid if we have to predict appreciation or like deflation or inflation. So those are even more out of our expertise as civil engineers. So all those are factors with deep uncertainties. So what we can do is, rather than trying to predict what is the exact risk, we want to come up with a model that can tell us when we will have unacceptable risk. So that's why on the right-hand side, you see, I want to have a model that have better interpretability to decide whether we have unacceptable risk than just purely to have a model to have good accuracy of judging if I have an unacceptable risk. So we use that for a very bread and butter structural reliability analysis. So that's where you see this, what we call performance function, where you have the structural demand coming from the AASHTO code as well as different climate relevant factors. And the one on the right in red are the resistance model to define what is the structural bearing capacity of this connector between the deck and the substructure. So what you see here is we consider these 5 different factors that we know may change under climate impact. We also know that at the structural level, at this structure, I have no way to predict accurately. I can give you a range of how those factors may change, but it's just impossible for us to know what will be the exact value. On the left, you see those pathways or potential life cycle risk profiles for this connector. So this is just to show that you have a wide range of possibilities for this specific structure. So what we are trying to do then is not trying to pick a line in this shaded area saying this is what's going to happen. So what we are trying to do is to see first, among all the factors with uncertainties, which factor is more likely to cause us unacceptable risk. So for that, we use samples from Loading hypercube sampling with an ensemble learning to rank the feature importance. So we noticed that the rate of a severe hurricane is the #1 factor that will cause unacceptable risk over the lifetime of a structure, followed by the surge, the storm surge heights under a hurricane. So the temperature, on the other hand, even though we know we are pretty confident this will rise by a significant margin, it's not going to impact the life cycle risk to a significant extent, in the sense that it will not likely to cause unacceptable failure risk. So lastly, not do we want to know which factor dominates, we also want to come up with some rules that decision makers can use to set up what we call climate signpost, so they can monitor over time to see what are the rules I need to monitor so that when this rule is violated, I need to strengthen this structure. So to do that, we use this technique called patient rule induction method to find simple rule to discuss what is the likely criteria that you want to follow to see when I need to do climate adaptation action. For this example, so you can see that we have the storm surge, we have the rate of hazard. So when the storm surge is increased by 7% or more, and the hurricane frequency increased by 2.7% or more, those are, if you are relatively confident about that 2 factors, you really need to strengthen your structure. You really need to either tie down your deck, otherwise you will have unacceptable life cycle risk under storm surge. So this pairs very well with the periodical review and updates of the climate projections from the IPCC, or Intergovernmental Panel on Climate Change. So what we propose is anytime you have a new IPCC report that gives you updated knowledge about what will happen in the future, you can update your belief of what will happen. In the previous example, you will have a more concrete belief of what will be the storm surge increase and what will be the storm frequency increase. So that will tell you if I reach that rule that I set up, so that I need to do climate adaptation actions. So that's our vision of how this can be used by decision makers to plan for the climate change despite the uncertainties involved. So with that, so the last slide is just a high-level summary of what I've been talking about. So performance risk assessment under catastrophic events. So those are events that are crucial for us to understand the societal impact of infrastructure disruption, because now we are actually analyzing a specific performance indicator relevant to the community. Second is there are challenges when you are trying to do the performance risk assessment, so mainly tied to the existence of grade 1 events as well as the curse of dimensionality. That means it's really hard to scale your analysis. So this is addressed in our research by the TMCMC. But we do need more research to see what will be the impact of different fragility models that you are using when you do performance risk assessment, and our group is trying to do that in a more detailed fashion currently. And for the climate part, we know that climate change may increase the frequency and intensity of a lot of the natural hazard. So in the example I gave is mainly on the flood and hurricanes. But we also need to realize that there are deep uncertainties when we look at only one county, only one structure. So then in that case, robust decision making is really, in our opinion, an effective way to make decisions about when we need to strengthen our structure. So with that, I think that's the last slide. I don't know how long I took, so apologies if I went overboard, but thank you for your attention.
Thank you
Yeah.
very much, Professor Yang. Thank you. Pues muchas gracias al profesor Yang por esta presentación tan didáctica, tan profunda y detallada. Le damos gracias por la oportunidad de conocer los desarrollos que ha logrado recientemente en la Universidad de Portland. Y con esto pues pasamos a la serie de preguntas y respuestas. Mientras nos acomodamos a ver si hay preguntas en las diferentes plataformas, yo quisiera hacer un par de preguntas. I would like to make you a couple of questions.
Sure.
First of all, IPCC considers scenarios for climatic change. Do they provide some information to consider the uncertainty of those scenarios, or how you take into account?
They do
that?
give you a confidence interval. So for the IPCC, can you hear me okay? That's okay?
Yeah.
So they do give you a confidence level interval of specific climate change impact. But the report itself, I would say, for practical use, is maybe limited because it's at very high global level, continental level. So if you are trying to do like a risk assessment, like what we did, what we presented here, so that information may not be super relevant to you, but I would say that that's still very useful because you can use those confidence interval level to put it as input for the robust decision making, so that you can try to. So we call those approach from global climate model to system to structural risk. We call the top-down approach.
Yeah.
So if you are not able to do top-down research, then you can always do bottom-up research. That is the second part of the climate model that we did. So just have some high-level, lower and upper bound of what may change in the future, and then you try to see which factor is more important, and then use that as your base for decision making. Does that make sense?
Yes,
Okay.
yes. Thank you very
Yeah,
much.
thanks.
My second question is talking about maintenance programs. In the first part, you were talking about the simplification of fragility curves and how can impact the different type of bridges. I understand that very important bridges, I mean the ones with the highest failure consequences, need to have a special treatment and be more careful avoiding these simplifications. However, some other bridges with not so high failure consequences may be treated with simplified models. But how come in this picture the monitoring? If you do some monitoring in the important bridges, how you can reduce the uncertainty and how you can improve the modeling?
Yeah, that's a great question. I think monitoring has a huge role to play. It will update your information. I think another contribution monitoring can make is, as you said, I think the main challenge may not be on those signature bridges, but for a lot of bridges that are very common, may not even have a detailed plan, design documents. So in those cases, monitoring can also be really helpful as well, in order to give you a baseline, in order to give you a lot of the material and dimension information that you can use to build your own fragility curve for that structure. One thing I do want to mention is there is some kind of conflicts between a really detailed fragility model with the regional level analysis that you see that I presented here. Because if you want to do regional analysis, usually it's the case you don't have all the structural details for all the structures in that network. So that's why we use hazardous model, because you only need information from what we call national bridge inventory. So the Federal Highway has a database of basic information of bridges, but you can't use those information alone to get a really structural specific fragility curve.
Yeah.
So if you want to do that, monitoring do help, but it's hard to monitor all the bridges in the network.
Yeah.
So I think both methods may have its place to have a significance.
Yeah, okay. Yes. Thank you, David.
Thanks.
Is there anyone with questions or comments? No hay preguntas, ¿no? Ahorita. One more question.
Yeah, sure.
If you want to do optimization under multiple hazards simultaneously, probably some people may say, well, the strongest hazard is not going to hit at the same time in the bridge. But there may be bridges with multiple hazards along the year, and it may be interesting to see how we can optimize the treatment to do an optimal maintenance for that bridge.
Yeah, I think I did some preliminary studies on the multi-hazard. So I do believe there are cases when multi-hazard can be analyzed in a more traditional way of load combination that has been kind of studied for a very long time in structural engineering, structural reliability community. But there are certain sequences of hazard that do have interactions that cannot be captured by those independent hazard models, such as scour and earthquake hazard. So once you have the compromised foundation, the seismic capacity may also drop. So in this case, when you do optimization, you would want to consider all those. It's potentially for a river crossing bridge, it's important to put those two factors into consideration. There is, I think we had a report, in our report we call this interacting hazard. So they may not happen at the same time, but over the lifetime, one hazard may damage structure in a way that will make the structure more vulnerable to an independent hazard. So even though earthquake will not triggered by scour and scour will not trigger earthquake, but they may have interaction in terms of the vulnerability of the structure. There is also what we call cascading hazard. So those are hazards that one hazard occurs and triggers another hazard. So typically people talk about cascading, that's a tsunami, right? So if you have earthquake damage structure through ground shaking, and then you have the huge wave that is trying to destroy an already weakened structure. So how to analyze those will be different from analyzing structure with ground shaking only, or structure with wave action only. So those are things you want to analyze together. So I think instead of Oregon, the cascading hazard that people have been analyzing is wildfire. So you see the example is in Pennsylvania, not in Oregon, because in Oregon, the main climate hazard is potentially wildfire. It still has flood, but I think for wildfire, that's the main thing that has been exacerbated by climate change. So once you have those burned surfaces, then you have a more likelihood for landslide compared to the vegetated one before the wildfire. So that's a cascading event as well. So there are my colleagues working on this, but I wouldn't comment too much because I don't know too much.
Thank you. Thank you so much.
Yeah.
¿Alguna pregunta, algún comentario del público de plataformas?
David, I have some question for the Professor Yang. I am Jorge Alamilla.
Jorge, gracias, adelante.
Yeah,
thank you.
First of all, Professor Yang, it's my pleasure to attend your conference. Thank you.
Oh, thank you.
I have some question. The first is I don't know. I want to know if you have some evidence about how the hazard curves are changing over time, and if these changes are important in structural engineering.
So the change, you mean the change due to climate change?
The modification of I am talking about the modification of the hazard curves.
Yes.
Due to climate changes.
Yeah.
Climate change.
Yeah, that's a good question, because like hazard curve was originally developed for earthquakes, and you wouldn't care too much about the changing, because it's not going to be impacted by the climate if you're talking about earthquake, I mean, in general. But I would say there are researchers talking about the non-stationary hazard curve that will change over time. So I would recommend you to follow some update from the Federal Highway website. So as far as I'm aware of, they are having an active project looking at the hazard curve for scour, considering the impact of climate change. So that may somehow answer your question. That is, how do I shift the hazard curve when I make the prediction 50 years down the road, 75 years down the road, or 100 years down the road? The short answer is I don't have a specific solution for you, but there are some excellent research going on. And apology that I cannot answer the questions directly. But there are, so I would say usually people shift the hazard curve. So you can parameterize how you shift your hazard curve and then do similar type of robust decision making to see what are the assumptions that are most sensitive for your risk assessment. Does that make sense?
Okay, thank you.
Yeah, thanks.
Thank you. I have another question about your fragility curve.
Yeah.
I couldn't hear, or I don't know if you can give some additional information about how the fragility curve or the failure probability distribution were obtained in a massive for a city, for example.
Okay. So there are different levels. So in one of my slides, I talk about different levels of complexity you can have for your fragility curve. And for the results we presented, at the city level, we mainly leveraged the fragility curve in HASUS, which is, I don't know if you're familiar with HASUS or not, so that's a system developed by FEMA.
Okay.
So over there, what you need is information from, as I said, National Bridge Inventory, or NBI. So in this case, all the data for potentially all the bridges in the US, especially state-owned bridges, you have information available. So you can use those information such as span, the width of the bridge, the type of bridge, the material of the bridge, to build your fragility curve to differentiate the vulnerabilities of the different bridges, even though you are analyzing for the entire city. So,
okay, thank you.
Yeah, so, but the caveat here, I wouldn't say the HASUS model is the most state-of-the-art. It's developed in 1990s, so there are a lot of things improving over the years. That's what we're trying to do these days, to try to use more advanced fragility curve, specifically what we call parameterized fragility curves or fragility surfaces, to better analyze the fragility. But I think the reason you ask is, when you have a more detailed fragility curve, you may not have all the information at the city level, and that's a challenge. But I would say a sensitivity study is the way to go.
Okay.
Yeah.
Thank you.
Yeah, thanks.
Thank you, Professor Yang. ¿Alguna otra pregunta o comentario del público? No, parece que no.
Yeah,
Bueno,
I also
sí.
have my emails there, so feel free to shoot me an email. I'm happy to discuss more online as well. Thank
Ok.
you.
El profesor nos ofrece, si deseamos enviar por correo electrónico preguntas, nos va a dar su dirección. Bueno, si no hay más, pues, démosle un aplauso otra vez al profesor Yang.
Thank you. Thank you
Gracias.
very much.
Thank you so much. Y ahora, a nombre de la Academia de Ingeniería, voy a hacer entrega este reconocimiento. As a token of appreciation, we
Thank you
want
very
to
much.
offer you this diploma. La Academia de Ingeniería otorga el presente reconocimiento al Dr. David Yang por su participación en la conferencia Performance Risk of Infrastructure Systems Under Catastrophic Events and Climate Impact, y firma el maestro Alberto Lepe Zúñiga. Muchas felicidades. Thank you very much. Congratulations.
Thank you very much. Thank you for having me. Thank you.
Gracias. Muchas gracias. Thank you.
Thank you very much.
Thank you very much. Thank you for having me. Thank you.
Pues con esto terminamos la conferencia del día de hoy. A todos, muchas gracias por su asistencia.